Hello, welcome back to the Thin Films course. My name is Professor Carlos Tavares and I am from the Center of Physics of the University of Minho. So on this chapter 3, we will talk about physical vapor deposition. Actually, in chapter 2, we talked about physical vapor deposition, but regarding a thermal evaporation process. In this chapter, we will be dealing with sputtering. So, as an introduction, physical vapor deposition can also be created. For example, when you have inert gas like argon, and if you have an electric field, you ionize this argon gas, and you will generate the plasma. And this argon gas, when it's ionized, so it's the valence is 1+, it will be attracted by a cathode. In this cathode, you will place a target of the material that you want to pulverize or to sputter. And these argon ions will impinge on this target and will create a cascade of collisions in this target that will eject atoms or molecules from the target, which will be transported onto the substrate and therefore will generate those nucleation mechanisms that I talked to you about in chapter 1 and 2, and you also create a thin film. So what is being read here in this slide is that so after being created this gaseous plasma, the gas ions, the working gas ions, which is the argon ions, are accelerated to this particular target. In this process, the target is warned by the ions, because if you have a very high flux of ions which is impacting on this target, it's natural that there's a wear on this target, because a lot of the constituents of the target atoms and molecules are being taken away. Okay, they are being ejected. In most of the cases, in normal sputtering, the ejected particles are neutrals. There is a parallel technique which is called high PIMS, which high impulse magnetron sputtering, where you can also pulverize ions. So a little bit of history. So the word sputter originates from Latin. It's sputter, it means to spit. It's not very nice. So this phenomenon was described for the first time 150 years ago by Grove and Pluck in the middle of the 19th century, when they reported the vaporization and subsequent formation of thin film by sputtering. It was important for the discovery of electrons and positive ions in the low pressure discharges through the Thomson and Rutherford experiments in the later part of the 19th century. So other names for sputtering is sputtering and cathode integration, which we normally don't use. We just use sputtering or pulverization, which is a physical vapor deposition method. As I said, you really need to have a plasma, and sometimes the plasma is called the fourth state of matter. So you have the solid, liquid, gas, and you also have a gaseous plasma, which is a very dynamic condition where neutral ions, where neutral atoms, ions, and electrons and photons coexist. So normally in the plasma, the resulting voltage or the total voltage is 0, because you have to add the ions, the positive ions and the electrons, okay, and the total charge should be equal to 0. So you really need an external power source, for example, radio frequency or direct current or microwave, to create an electric field or an electromagnetic field, okay, in the case, for example, of RF and microwave, in order to maintain this plasma, because you have to continuously ionize this inert gas, so it can generate the monovalent ions and the electrons that will sustain the plasma. So this dynamic state can be maintained by introducing a controlled form, a noble inert gas, for example, argon, helium, xenon, and krypton. For example, here on the bottom part, you can see the plasma which is created in a lightning storm. Okay, so normally, how is this generated? Basically, for example, if the base of the cloud has an accumulation of electric charges, these negative electric charges will make a repulsive force on the electric charges, which are also negative, that are on the surface, and they will to attract the positive forces. So you will have an electric field between the base of the cloud and the ground. Now, for the current flow from the base of the cloud to the ground or from the ground to the cloud, there is an important thing that has to happen. So the electric field must be higher than the dielectric strength of the air, okay? And which is millions of volts per meter. And so, and if the electric field is high enough, then it will break the dielectric properties of the air and will find a way through this path, okay, to reach the ground for the charges to flow. And along these branches of what we call lighting, we generate a plasma because we ionize in the air, we generate ions, and we also have electrons. Here you can see a plasma which is generated inside the vacuum chamber. And we, in this case, the gas that we used was helium. Now is an example of sputtering in one of our systems that we have at the Center of Physics at the University of Minho. So before running the video, I'm just going to show you here a magnetron, and I will explain later on what is a magnetron. But anyway, here on the surface of this magnetron, we put the target material. So the material that we want to use as for sputtering. So it means that the atoms or molecules that will be ejected from this target will be deposited on the substrates, which are rotating in this case around this target. So the flux of atoms will leave the target and will be impinged on these substrate holders, and the atoms hopefully will have enough energy and surface mobility to reach nucleation sites and condense and form the growing film. Okay, so I'll run the video. Okay, and now it's another example. We use a glass chamber, a bell jar, and we have also magnetron here. So we have a cathode. So this is the negative part of the process. So it's the target is connected to a cathode, which and so the cathode is the negative electrode, which is connected to a DC current power supply. It will have to generate around 500 watts. So it's the 500 volts times 1 ampere, so it's 500 watts. And here's the anode, the positive electrode. So in this process, we connect the electrode with the cathode and the electrode with the supply. And how to do it 3 times 10 to the minus 3 millibar, which means it's something like, well, it can be around, it's a relative pressure or partial pressure, which is almost 1 million times lower than atmospheric pressure. And so when you create these conditions, you ionize the gas, and you will have this the helium ions, after being ionized, they are acting on the target. We are ejecting atoms from this target. Okay, in this case, I think it was titanium, and the titanium atoms are then ejected vertically toward us onto the substrate holder. So sputtering is a technique which involves physical deposition, and it's used many applications in the industry for the synthesis of thin films. Many applications include, for example, metal layers for metal contacts in electrodes. Also, in most cases, for wear prevention on tools, like for example on screwdrivers, on drills, on cutting tools for metal sheets, you need to apply on the base material, which normally is stainless steel or some kind of hard steel. You need to put a very thin coating, for example, titanium nitride, titanium aluminum nitride, or carbon, or for example, chromium nitride, to enhance the mechanical properties in terms of resistance to wear. For example, if you want to make a coating, for example, for a door handle to open the doors, and you know, sometimes you have sweat in your hands, or your hands are dirty with debris or some kind of acids, And if you put your hands on the doorknobs, with time, the surface of the doorknob is oxidized. But if you make a coating, for example, chromium nitride, it can resist this wear that you have on your hands from the sweat, etc. And or another case, so this is the type of coating chromium nitride. For example, titanium nitride is the coating that I would choose for a hard coating. For example, it has a very nice gold color, and you can put on drills to enhance the lifetime. Titanium aluminum nitride, well, it's also a nitride. It's a bit similar to titanium, but for a specific composition of titanium aluminum, it will actually enhance the mechanical properties for high temperature applications. For example, if you're using a mechanical tool which is subjected to high temperature, for example, for drilling, for cutting, where temperature can exceed sometimes 1000 degrees or 800 degrees, then the aluminum will help the coating to resist more to oxidation at elevated temperatures, okay? And boron nitride, when it's in a cubic form, it's a very hard material. I think it's the second hardest material, just below diamond. Diamond is the hardest material, but when you do this by sputtering in a cubic form, it's really, really very hard, okay? And some oxides can also be produced by sputtering. For example, titanium dioxide, which is well known for its self-cleaning property. It's a photocatalytic material. It means that when it's irradiated with light, with an energy just above its semiconductor band gap, it will generate photocatalytic mechanisms, which is a mix of oxidation reduction reactions. So you have a generation of superoxide ions and hydroxyl radicals. For example, if this material is in contact with water, and these hydroxide radicals have a very oxidizing potential. It's about 2.8 electron volts, and can mineralize, for example, pollutants which are absorbed on the surface, okay? Or can even attack bacteria. So you can have a self-cleaning antibacterial surface if you produce this kind of coating. You can also put zirconia, zinc oxide. It's also very interesting, for example, for gas sensing. ITO, it's actually an abbreviation form for indium tin oxide. It's an interesting oxide which is transparent, but it's electrically conductive. So you imagine if you have a window, okay, of glass, and you apply this coating, this ITO, so indium tin oxide, and then you have an electrode. So you will have a thin film which is conducted, and you can place electrodes on this glass, okay, or iron oxide, etc. And you can do these kind of coatings on glass, silicon, metal, plastic, textile, ceramic, etc. You have to be careful when you're working with plastic and textiles, because the physical vapor deposition is a process which involves generation of heat, because when these argon ions are impacting on the surface of the target, due to the transfer of momentum and kinetic energy, you also have generation of heat on the surface of the target. And so if the flux of atoms that is ejected from the target is very high, it will impinge on the substrates. And if they're made of polymer or textile, you can easily burn them, okay? Or damage its inherent properties. So in most cases, reactive magnetron sputtering is actually comprises about 90% of the applications in PVD systems. So reactive sputtering means that you have to introduce a gas to form a compound. For example, if you're, in this case, if this target is titanium and you want to make titanium dioxide, then you have to introduce oxygen in the process besides the argon. So there are two gases that you have to introduce. You cannot generate a plasma if you do not introduce, for example, argon or krypton or xenon, which is an inert gas, okay? Then if you want to make reactive sputtering, then you have to introduce oxygen if you want to make titanium dioxide. But if you, instead of making titanium dioxide, which is this compound, if you want to make titanium nitride, then you don't need the oxygen, but you need nitrogen. You introduce nitrogen, okay? If you want to make, for example, titanium carbide, then there is no gas solely comprised of carbon atoms. You have to introduce a gas which has carbon, for example, methane or acetylene, which can be used, or CO2. You can introduce this gas, and the carbon will be used to make the bonding between the metal, well, to make the bond with the metal, of course, and to make this titanium carbide coating, for example, okay? And in some applications, you can also do amorphous carbon coatings. for example, for some specific components of the motors where there's a lot of wear, and you need to, for example, the pistons of the motor in the car, there are certain parts in this piston where the friction coefficient has to be very, very low. So you will not have a lot of wear, so you will not damage the piston. And some coatings which involve carbon-based coatings, like diamond-like carbon coatings, they have a very low coefficient of friction, and they will help increase the wear resistance of the coating material on these steel parts or the aluminum parts of the motor. So for now, maybe I have said some things that you probably don't understand very well, but hopefully at the end of this talk you'll understand everything that I've said so far, because I'll give you particular examples for everything that I've said so far. So let's look at the initial part of the sputtering. So you have argon gas, for example. Let's take into account that our working gas is argon, okay? So it's the gas that will be ionized and will generate the plasma. So if we take argon as a working gas, we have to have the electric field, okay, between the cathode and the anode, which will ionize the argon and will create argon plus ions and electrons. And the electrons are necessary to continuously ionize the argon, okay? So when this argon ion is ionized and it has a positive charge, okay, as you see here, it will be incident on the surface of your target, for example, titanium target, okay, which is what we're seeing here, okay? And in this process, if it has a high energy, and it can have an energy of up to 500 electron volts, for example, okay? So if the voltage between the cathode and the anode is 500 volts, and you have one ion, which is has a charge of 1 electron plus, okay? So it means that the potential energy is 1 electron times the voltage. So it's 500 volts times 1 electron, so it's 500 electron volts, okay? And so this is a very high energy. If you compare it to thermal evaporation, I told you that the maximum energy would be about around 1 electron volt, but in most cases it's about 0.5 electron volts, okay? So, and when this ion impinges on the surface, it has to have enough energy, and more energy than the bonding energy of these atoms of the target, okay? And if the energy is higher, it will create this cascade that you see here, okay? So the argon ion it's like snooker game, this game that you play with the stick, and you have the balls on the green table. You hit the white ball, and the white ball will collide with the other balls on the table. So it's the same thing. It's ballistic, okay? So this argon ion hits the surface of the target. It ejects atoms, which in most cases in normal sputtering are neutrals. And in the process, these blue atoms, so it's imagine the tiny atoms of the target, will also release some electrons, and these are secondary electrons, okay? And these electrons are very important to continuously ionize the neutral argon ions, which are around the target, and they will become ionized, they'll become red, okay? Like, as I'm saying here, just as a graphic explanation. And then they will hit again the surface of the target continuously, and they will eject more atoms, which will be then forward towards the substrate, okay? So in the schematic, you see what we see here on the surface, okay? So we have atoms of the target material, okay? So when the argon ion is incident through this transfer of momentum and kinetic energy, it will eject these atoms, and they are called sputtered atoms, okay? In some cases, so this argon ion, which it needs an electron to become neutral, can capture one of these secondary electrons and becomes neutral again, okay? But it really needs to be ionized again, okay? So it will have sufficient energy to be accelerated towards the cathode, because if the argon atom is neutral, it will not be attracted by the cathode. It has to be an ion it has to be positive to be attracted by the negative potential of the cathode, okay? And it will collide very fast with a high energy, enough to break the bonding between these atoms, and so it's a knock-on that you see here, ballistic, and will eject these sputter atoms towards the substrate. So let's look here at this this website, which has some Java applets that explain very well the process of sputtering. So I'm going to open this link and hopefully I hope it opens. Okay. So let's see here. I'm just going to increase here the view range of my window. Maybe I expanded too much. Okay, you might lose resolution. Okay, so let me first explain what we're seeing here. So here we have a target. Okay, so imagine it's the titanium material that we have on the target. So these yellow atoms are the target material. The red ones are the argon atoms, the neutron that are being introduced into the chamber, normal with a pressure which is about 1,000,000 times below atmospheric pressure. But remember that before starting this process, the pressure inside the chamber has to be 1,000,000,000 times below atmospheric pressure at least. So 10 to the minus 6 millibar. Okay, and when you introduce the argon, you increase the pressure 1,000 times in this process. Now it's 1,000,000 times below atmospheric pressure. So you really have to have a primary vacuum system and a secondary vacuum system. Normally you have to have a rough pump that lowers the pressure about 10,000 times in respect to atmospheric pressure. Then you need a turbo macro pump or a diffusion pump to continuously make more vacuum and decrease the pressure until you have about 1 billion below atmospheric pressure. So let's concentrate on these atoms, which are neutral argon, which is being introduced into the chamber. The blue particles are electrons, and the pink particles are argon ions. It's when this argon neutral atom is ionized and becomes monovalent. Okay, so let's see here the process which involves the ionization of argon. Okay, so we have this neutral argon atom which is running around. Okay, it's not attracted by the cathode, but as soon as it is hit by an electron, it becomes ionized, becomes positive. And when it becomes positive, it's attracted by the negatively charged electrode, because when it's neutral, it's not attracted. So I'll run it again. Okay, see, it's not attracted now by the target, which is negative. Look what happens now. Okay, it becomes an ion and it's attracted. And if you look closely, see what happens here. When it hits the surface of the target, okay, when it turns pink, ionized, it will eject atoms. You see these yellow atoms, which are from the target. Okay. So now let's see what happens when these ejected yellow atoms from this target material are transferred to the substrate. Okay, look closely, please. So we have the argon ions impinging on the target. These atoms are ejected and they will go to the surface of your target. So it's the component that you want to coat. Can be a flat plate, can be a glass slide, a silicon wafer, can be a textile sample, can be a hard steel disc, can be even a three-dimensional part. Okay, actually sputtering is not the best technique to make depositions on three-dimensional parts, especially if they have cavities, because you will not have a uniform coating. Atomic layer deposition is much better for that. We'll be talking this in the next chapter. Okay, but anyway, look again. You see that the argon ions eject atoms, neutral atoms, which are projected or sputtered towards your substrate, and they will absorb on the surface. Okay. Now let's see another process, which is the maintaining of the plasma, because these argon ions, they became these argon atoms, they became ions, they became positive, but we really need to have more argon neutrals which have to become ionized. Okay, because we want to continuously remove atoms from the target. Okay, and this process, you see, look what happens now. Did you understand? So I'll repeat it. So we have, what we'll see is two argon ions which collide with electrons, and they become neutrals again. And when they become neutrals again, they will release the excessive energy in terms of photons. And these photons will emit light depending on the type of gas. For example, in my experience, if you use argon, this plasma is generated by these photons that you see here that emit in the range of UV and violet. Okay, so so the plasma looks violet, as you saw on the previous process. If it's nitrogen, if you can also ionize nitrogen as a working gas. Normally, nitrogen is used as a reactive gas, but you can also make a plasma with nitrogen or oxygen, and it has actually a more red color between violet and red. Okay, so between violet and red, you can go from blue to green, to yellow to orange and to red, but you have a mixture of this of violet and red tones. Okay, if you have, for example, a helium gas and you want to ionize it, you will have a kind of blue-green plasma. Okay, so let's see again the importance of this process, which involves the generation of these photons, which will maintain the plasma. So you see the electrons hit the ions, and you have neutral atoms. So, and these neutral atoms can be further ionized in the process. Okay, and one way to do this is to put some magnets below the target, so that you will create here some magnetic traps to capture these electrons. Imagine that you have an electron running around here. It's important to have electrons not here in this space between the target, which is here in the bottom, and the substrate. Take into account that in most cases the distance for normal sputtering in laboratory equipment, normally the distance between the target and the substrate is around between 6 to 15 centimeters. Okay, for example, in my case, the distance in our systems is about 8 centimeters. For larger systems, it's about 15 centimeters. But in industrial cases, you might have larger distances. The distance has to be more or less of the order of the mean free path of the ejected particle, so that it will not collide with other particles. So they have a direct line of sight towards the substrate, and they will condense without losing energy in the process. Okay, so but let's go back to this electron. I don't want it to be here. I need it to be here, closer to the target, so it can ionize the argon gases, or the argon gas atoms which are running around here, okay, closer to the target, so they will have more energy when they're ionized and closer to the target. They will eject these atoms of target more easily, because they will have higher energy than if they were placed further away. Okay, so what we do here, we put magnets with reverse polarity. For example, here, imagine, for example, north of the magnet is facing up, here the south is facing up, and north is facing up. So you create magnetic field lines. And remember that contrary-wise to electric field lines, the magnetic field lines do not start or end in specific points. They are closed lines, okay? So these lines are closed, okay? So what we have here is the magnetic field lines. And in this process, we create these traps because we have to, we have an electric field which is generated between the negative part of the process, which is the target, and the substrate is polarized with the positive polarities. So you have the anode here and you have the cathode here. So you have an electric field which goes from the highest potential to the lowest potential. So the electric field points downwards, okay? And if you concentrate here, so the electric field points downwards, and if you look at this point, the magnetic field is tangent to this line, okay? So it can point to the right or to the left, or can point towards the inside of this your screen or towards you, okay? And you have to use Lorentz law or the Stirling law with, for example, for the magnetic force. If the particle is positive, then you should use your left hand. So it means that the magnetic force is a vectorial equation, and from this vectorial equation you have that the magnetic force is the charge times the velocity vector times the magnetic field vector. So this, your thumb gives the direction of the magnetic force, your index finger gives you the direction of the velocity of the charge. If it's an electron, it's negative, and the middle finger gives you the direction of the magnetic field. So you can place this hand, your hand there, and you have an idea of how the force interacts with the charged particle, okay? If it's a positive particle, you can use your right hand for this same thing. Okay, but anyway, and if the magnetic force here is equal to the electrical force, So going back again, the electric force is the charge times the electric field. So it's Q times E vector. And the magnetic force, it's Q, which it's the charge, times the velocity, times the magnetic field. It's a vectorial equation. So the magnetic force is actually perpendicular to the plane formed by the velocity and the magnetic field. Okay. And when these two forces are equal, you can, if you put them in an equation, you can get the charge from both sides. So you have the electrical field equals the velocity times vectorial notation, the magnetic field. So E equals V times B, which is the magnetic field, or the magnetic flux density. And within this, you will have conditions that will make that the electron, and when it enters this magnetic field, it will be obliged to have this kind of cyclodal movement around the magnetic field line, so it will be trapped, okay? But it's better to look at what happens here, okay? See the electron, nothing is happening to the electron now, but when it enters this magnetic field line here, okay, it does this cyclodal movement due to that the electric field equals the velocity times the magnetic field, okay? So we have another argon atom, sorry. It will become ionized, okay? So it's important to have these electrons here, which first will ionize the argon atoms, and then we'll turn them into neutrals again, okay? And you need to have the argon ions so they can impact on the target, because if they are neutrals, they will not have attraction to the target. See the electrons again, they are trapped. Then here comes an argon atom, okay? It's neutral, okay? And when it enters this place, here, this zone, okay, it will become positive and will be forward to the target, ejects atoms. Then it can be ionized again, okay? You see? So this process to be continuous in order to maintain the plasma. So here we have a process which has actually 3 magnetrons. You can have a system with more than 1 magnetron, okay? And you're sputtering, for example, for 3 different materials or for 3 different compounds. You can also change the angle between the cathode and your direction towards the substrate, and also the substrate. This is between the cathodes. We have 2 cathodes here and the substrate holder, okay? And here is another process for sputtering. So let's go back to the presentation that I was giving you. Okay, so we will continue talking about sputtering. Here you can see a sputtering system which you can find in some laboratories. Actually, I wish I had this one, which I said mine, but actually, so what does this involve? Well, it involves a chamber. Actually, you have 2 chambers here. So this is where the sputtering occurs, and you have a door, which is it's a door or a gate valve here that will open or will have, you can give you access to the inside of the sputtering chamber, because normally you load your samples through this door. So it's a loading lock here, okay? And when you open this part, inside here it will be atmospheric pressure because air will come in. So you have to close this to always maintain the vacuum inside your main zone where you make your deposition. So you close this gate valve, okay? You pressurize here, you open this door, you put your samples in, you make a vacuum in this part, and when the pressure here is more or less the same as it was here in the deposition chamber, then you open the gate valve, you transfer your samples with a transfer mechanism towards the inside of your sputtering machine, you close the gate, you make the deposition process. After the deposition, you open back the door, you put your samples here, you close the gate valve, you pressurize this part of the chamber, you open the door, and you take out your samples. So of course you need power supplies to connect to the electrodes, to the cathodes, and to the anodes, and you need to have a computer-aided software. So you perhaps, if you do this process many times, you need to have some kind of recipes for doing if you have multiple types of layers. If you use different targets to make complex coatings, then it's important to have some kind of system which you have these routines or these recipes which you can just press a button and produce them, or you can just use the software to experiment and try to change some parameters, like for example the pressure for the working gas, the pressure for the reactive gas, the power that you need, because normally you don't know beforehand. It's always tricky when you start to make a new coating for a specific application. Sometimes, for my example, I have 26 years of experience in PVD systems. So sometimes you can take a few months just to optimize the process condition to make a specific coating. It's not very easy and straightforward. So you have to waste a lot of time. And now I'm going to talk to you about the advantages of sputtering, and also talk to you about the disadvantages. But so some of the advantages are you can do mono-elemental materials, like you just can produce a copper coating, or you can do alloys, complex compounds that can be deposited as coatings. The sputtering target provides a stable source and a dilated lifetime. In some configurations, the reactive deposition can be performed using reactive gases like nitrogen, oxygen, silane. Silane is important if you want to have the silicon. Silane is silicon SiH4, and so if you want either hydrogen or silicon from this precursor, you can use the silane. Or if you want to make a reaction between the, for example, metal and carbon, you can use acetylene or methane, which will give you the carbon part and some hydrogen, which are activated in the plasma. This target, here's a mistake. The source target and substrate holder are very close, between 5 to 15 centimeters. Yeah, I have here 10, but in most cases it can go up to 15 centimeters. And the piston chamber might have a small volume, because, for example, ours is about 40 centimeters tall and 45 centimeters in diameter, so you have an idea how big it is, okay? And we have about 8 centimeters distance between the surface of the target and your substrate holder, okay? And one other big advantage, which is perhaps not here when I should talk to you about, is that you don't use any chemicals. Okay, so it's a very environmental friendly technique, because in this course I'll be giving you, I will be talking about production of films either from a chemical or a physical vapor process. I will not talk to you about, for example, sol gel films, which is a wet process, wet chemical process. Okay, so I'll be talking about only vapor phase production of films, which includes PVD, physical vapor deposition, chemical vapor deposition, and from the PVD you also have the thermal evaporation, and also from the CVD you also have the ALD, which is atomic layer deposition. Okay, but no wet chemical synthesis. Okay, so we didn't use any in this process. We didn't use any acids, any reagents. So besides the gas, okay, and we need reactive gas, which is nitrogen, oxygen. And for the sputtering, we use inert gas like argon, which is the most cheap and versatile gas that we can use, okay? But now some disadvantages. The deposition rates are low when compared to with systems such as thermal evaporation, which we saw in the last talk. Thermal evaporation gives you coatings which are much thicker. You can reach tens of microns with the thermal evaporation, but the coatings do not adhere very well to the substrate, and you can scratch them off easily, okay? So for mechanical application, you forget about thermal evaporation. It's easy, it's very good to produce mirror surface, for example, in the optics of the cars, for mirrors, even for Christmas balls. You know, these balls now, you can put on your Christmas tree. You can use thermal evaporation to produce very nice colors on these plastic spheres for the Christmas tree, for just an example. Or you can use it for other processes, which the coating is protected and will not be subjected to wear or to erosion, okay? Depending on the target material, the target is going to be very expensive. I mentioned yesterday that I bought a palladium target some years ago, which costed me about $5,000. It was 5 centimeters in diameter and 3 millimeters thick, I think. Okay, so it's very expensive. depending on the materials. But for example, a titanium target with a 4-inch or 10 centimeter diameter titanium target with 6 millimeters thickness can cost about 250 euros. Okay, so and they last a long time. In some cases, these targets can last 2-3 years just for laboratory work. While others are more expensive. For example, targets that can produce transparent conductive oxides, like for example the ITO, the indium tin oxide, can cost about 800 euros for the same size, about 10 centimeters in diameter and 6 millimeters thick. Okay. So another disadvantage, most of the energy of the inside ions is transformed into heat. So you have to cool the magnetron. You have to cool the undersurface of the target, because in some cases, if the heat is excessive, it can damage the target. It can damage the magnetron, because you remember that in the magnetron, we need to have magnets, okay, to create these magnetic field lines. And if the temperature of the magnetron exceeds the Curie temperature of the magnetron, the magnets, then the magnets will lose its magnetization, because the Curie temperature of a magnet is the maximum operating temperature that the magnet can withhold without losing its magnetic properties. Okay. After that, the magnetic susceptibility is destroyed, and so you lose the magnetic flux that you had in these magnets. Okay. Another disadvantage is that the reactive gas partial pressure must be accurately controlled to avoid poisoning of the target. What does this mean? For example, if you're using oxygen as a reactive gas, we want the oxygen to bond with the ejected particles that come from the target. So if you have titanium atoms and you have oxygen and you want to make titanium dioxide, you need to have the bonding, the chemical reaction that makes the bond between titanium and 2 oxygen atoms to make titanium dioxide. And you don't want this oxygen to cover your target. You only want the oxygen to react with the ejected titanium atoms and not with those which are in the target. Because if you have a covering of oxygen on the surface of your target, then you have the electric layer on top of your cathode, and hence the electrical field will be reduced, and you will not ionize so easily the argon atoms, which is the working gas. Okay. You can do nice things with sputtering. For example, you can make this kind of chevron zigzag structures. For example, if you continuously rotate your substrate holder like this, okay, and you have a constant flux of particles, and if you constantly rotate it, you can have this kind of chevron structure, which you can read here, for example, from this paper, which is very interesting. Okay, but now I will give you some aspects of sputtering, how it started. Okay, because the first sputtering experiments were actually done within a light bulb. If you remember those very old light bulbs, which hopefully maybe you don't have anymore in your houses. Now you either have fluorescent lights or have LED lights. But in 20 years ago, maybe at that time, in most houses you would still expect to have incandescent lamps. These lamps which have a filament. And these lamps have a very low efficiency, because most of the converted energy that you can in an electrical incandescent lamp, you transform electricity into light and into heat. And the component of it is very big, because if you would put your hand on these incandescent lamps when they were running for some time, they would be extremely hot. You couldn't burn your fingers, okay? Because a lot of heat was wasted a lot of energy was wasted by heat, okay, due to the Joule theory, because the power which is dissipated is proportional to the resistance times the square of the electrical current, and there's a lot of dissipation of energy, and due to the Joule effect, you have a lot of this energy transformed into heat, okay. And of course, if the lamp is not efficient, then only a small part of the power which was given to the lamp will be used to convert it into photons, into light. Okay, so it's always important to of course, to use in our houses lamps which are more efficient, for example, LED lights or fluorescent lights. LED lights, they are very efficient. If you put your hands on an LED light, you will see that it's not very hot, okay? If you put your hands on a fluorescent lamp, it's a bit hotter than the LED light. And of course, in incandescent lamps, they are much hotter, okay? But now I remember what I was talking about. So for a few seconds, I forgot about. So I was going back to the process of the first events of sputtering, which were done in these light bulbs, in these first light bulbs, which are filament light bulbs, incandescent lamps. So you would have, for example, a tungsten wire inside this glass bulb, and you would pass a current through this filament, and you would have vacuum in this bulb, okay? So what happens is that when this current is passing through the filament, it will also can eject some atoms of tungsten. And so these atoms that are ejected will coat the inner side of the bulb, okay? And in this process, you're actually making a physical vapor deposition. And this is what happens with bulbs when they reach their lifetime, when they cannot emit light anymore. For example, in the cars, some cars actually still use incandescent lamps. For example, if you change the lamp of the signal turning lamp of your car, or the headlights, some headlights are still incandescent lamps. Not all cars still have LEDs yet, or these lamps that give the red color in the back. Okay, actually they're normal lamps, but you have a red reflector or a plastic which transmits red light. Okay, so if you change the lamps, and if they're old, that they're not working anymore, you see that the inside of the lamp is black. Okay, because there are sputtering of atoms from this filament, which will coat the inner side of the glass. Okay, so the first basic diode sputtering consisted of a sputtering experiment where you don't use a magnetron, you just use a cathode. So this is the most easy process to do sputtering. You just have a target with your target material, for example, titanium or aluminum, whatever, okay, which you will connect to a DC power supply, a direct current power supply. So this will be connected to the negative electrode, and the positive electrode is your substrate holder. It's the material that you want to coat. So so here is the anode, and this is the cathode, okay? And in between, you can put a gas, which is, you will have to put an inert gas, which can be ionized, for example, argon or xenon. And when the argon is ionized, well, you will have the electrons, which are necessary to continuously ionize the argon gas. You will have the neutral atoms, which are being sputtered. And you have some kind of residual gas, because even when you're working at 10 to the minus 6 millibar, you cannot say that you have complete vacuum, okay? Because you still have a residual gas, you still have some water vapor, you might have some carbon dioxide. For example, in the CERN, in Geneva, in Switzerland, in this accelerator that you have there, you in the ring where you make these experiments, you have to have a pressure in the ring which is about of the order 10 to the minus 12 millibar, okay? So it's 6 orders of pressure below what we would need to have before doing a sputtering experiment in one of our main equipments in the laboratories, okay? And so this is the easiest process, and you have an electric field between the anode and the cathode, and you can produce this kind of sputtering, okay? But this sputtering process is not very efficient. It requires higher pressures, okay? So you can only do this diode sputtering at pressures around 10 to the minus 2 millibar, or in the range of 10 to the minus 2 to 10 to the minus 1. So between 100,000 and 10,000 times below atmospheric pressure, which means that the background gas can be a lot. You might have oxygen, water vapor, carbon dioxide, and this, of course, will impact on the purity of the material that you're going to deposit, okay? So in order to lower the pressure, you need to have another type of sputtering, which involves using the magnetron to more efficiently ionize the argon, okay? So this is DC sputtering, because you use just a current which is given by a DC power supply. A DC power supply gives a current which is maintained with time, okay? It does not change. For example, you can have also an AC power supply, alternating current, and this will give a modulation to the current in the form of a sine wave, as you have, for example, in the AC outlets that you have at home to connect, for example, the power supply of your computer, because the current that is being drawn from these power sources that you have in the wall that you can connect your electrical supplies, they have an alternating current or alternating voltage. For example, in Europe, in most cases, we have 220 volts to 240 volts, and it's a sine wave with a frequency of about 50 hertz. But if you go, for example, to the United States, it's 110 to 120 volts, and the frequency is 60 hertz. Okay. So if you look now at this process that I'm showing you here, it's alternating current, but it's provided by a radio frequency sputtering. So what's happening is that instead of having DC, we have alternating current, which means that this positive and negative is changing with time. And if you use, for example, this kind of a generator, it can change between positive and negative 13.5 million times per second. If you use a 13.5 megahertz frequency, I think it's this kind. Yeah, yeah. So it's 13.56 megahertz. Okay, so it means that the positive and the negative electrons are being switched 13.56 million times per second. Okay, and why we are doing this? Why are we doing this? Because, like I said, we have to avoid, if you're doing, for example, reactive sputtering, we have to avoid the accumulation of oxygen on the target surface, because then you will shield this electric field. Okay, it will cease to have such a high intensity. So in one polarity, you will attract argon ions. So when the polarity, if it's alternating in the negative polarity, you will attract argon ions. Okay, and on the positive polarity, you will deflect them, you will repulse them. And by doing this, you can also make some impact in reducing the possibility for oxygen atoms to be adsorbed on the surface and to poison your target, literally. Okay. And so in this case, we have the target. So it's what we have here, the target. Okay, it's here. It's connected to a radio frequency power supply, which is alternating current. Okay. Then you have your substrate holder. You can put more than one substrate, the materials that you want to coat. You have a gas. You need to have gas bottles for the argon, for example. For example, if you want to make only titanium films, not titanium dioxide, only titanium, you just need to have titanium target. You have to have the argon gas, and the argon gas is fed by a device which has a solenoid which controls very small finite amounts of gas. It's an MFC, it's a mass flow controller. And this mass flow controller can, for example, it will enable you to put inside fluxes in the range of, for example, for argon, we should use more or less between 30 to 60, depending on the applications, cubic centimeters per minute, or 30 to 60 milliliters of argon gas per minute. Okay, so it's very few, and it really depends on your pumping system. Okay, depends on the pumping depends on the pumps that you have. Depends on your pumping speed, and if, of course, you have to obviously fine-tune these conditions in order to take the most advantage out of your sputtering process. Okay, and additionally, the radio frequency, the power supply, is actually more important when your target is not conductive. For example, if you're using titanium, it's conductive, it's okay, but you can still use radio frequency, it's no problem. But if you're using, for example, a polyamide target, you can also use a polymer target to sputter polymer chains. Okay, if you're using, for example, a polymer or silicon, which is also not a semiconductor, it's not very conductive. If you use silicon target, or if you use a polymer target which is non-conductive, then diode sputtering will not work. Okay, because if it's an insulator, then you'll have accumulation of charges here, and they will make a shielding to your cathode. Okay, But if you use an alternating current, then in one polarity, you will attract these charges, and on the other polarity, you will repulse them. Okay, so and you will avoid this shielding of your target. Okay, and this is why we should use radio frequency sputtering when we're thinking about sputtering from insulators. Okay, from targets which are non-conductive. Okay. So if you want to use a reactive gas in the process, you have to have another bottle for the reactive gas, like for example, for acetylene, provide a carbon, or for nitrogen, or for oxygen, okay? And for each of the gas bottles, you have to have specific mass flow controllers, which are calibrated for the type of gas that you're going to use and have a range of opening of the solenoid valve, which is appropriate for the inlet amounts of cubic centimeters per centimeter, which we normally say SCCMs or milliliters per minute, that you want to introduce into your system. There are differences between using low frequencies and high frequencies, okay? And let's see, why do we use such a high frequency when we use, for example, RF sputtering? It has to do with the dancing of the charges and the particles inside your chamber, because for frequencies below 50 kilohertz, when you're using AC power supplies, the electrons and the ions of the plasma become mobile. So the alternating electromagnetic field will not impact not only on the electrons but on the ions. Okay, so it's basically a diode sputtering. And so because what does it mean impact? It means that both the electrons and the ions are swaying, are dancing with this alternating potential, okay? And so they sway along to this potential. And we want to avoid this because, you know, ions are much heavier than electrons. For example, the mass of a proton is 1.67 times 10 to the minus 27 kilograms, and the electron is 9.11 times 10 to the minus 31 kilograms. So you see, the electrons are very light in comparison to a proton, and they're much lighter than neutral atoms, okay? And so we need to have frequencies above 50 kilohertz, so the heavier ions will not sway to the rhythm of the source, okay? And so we only want to attract and repulse these electrons when we use the insulator targets, okay? So that they will not have a shield on the surface of your magnetron or the target, okay? And normally, if we really need to have frequencies around between 5 and 30 megahertz to efficiently only sway the electrons, and so that the ions will not be mobile, will be unaffected by this alternating electromagnetic field, okay? So, so this frequency is important for targets which are insulated, which are the electrics. You can sputter glass materials, ceramic materials, and these are the electrics, and you can only do this with the radio frequency sputtering, okay? And it will orientate the plasma more closely to the target, and it also enables operating at lower pressures in the range of 10 to the minus 3 to 10 to the minus 2 millibar. This range of pressures is very important because those people who work on sputtering, they normally work within this range. So this, if you compare this to atmosphere, it's between 1 million times and 100,000 times lower than atmospheric pressure, okay? So let's look now at more aspects of magnetron sputtering. So as you can see, we can either use DC, okay, or we can use RF. And it really, the importance of doing this, you have to check if you're using insulator target or metal target, sorry. A metal target, you can use DC. If you're using an insulator, you have to use RF. And this is always important to enhance the efficiency of the pulverization, because there are ways to increase the ionization of working gas. So you will obtain high deposition rates at low pressures, around 10 to the minus 3 millibar. Because in this range of pressure we have fewer collisions, so you'll have the sputtered atoms will have a longer mean free path between collisions, so it will not lose much energy in the distance that goes from the target to the substrate. It can be only 10 centimeters, but it's really crucial, okay? And it also increases the probability of electrons in ionizing the working gas, can be argon, helium, etc. So let's look again at a magnetron, okay? So you have your target material, and these magnets that you have here will create these magnetic field lines. And of course, if you are making a sputtering, so these argon ions which are impacting on the surface of your target, they will erode the target with time. And they will erode more. You see that the thickness is not uniform. You have this kind of U shape here, okay? This means that there are many target atoms which have been ejected, and so the target has become worn. You see here, okay? And this is one drawback of magnetron sputtering, is that in time you actually lose your target material, okay? And it's the erosion is bigger, much bigger in this direction, where you have the higher magnetic flux density. So we also have a higher probability of argon ions impacting on the target surface, okay? And you can see this here. For example, this is the magnetron. So you place the magnets in the bottom. You have to have water cooling, like I mentioned, because the water has to cool the magnets. Otherwise, if the temperature is very high due to the impinging argon ions, it will destroy the magnetic properties of the magnets. Here you see the magnets with their polarity, okay, north, south, north, or maybe the other way around, south, north, south, okay, to create these magnetic field lines. You have the plasma within these magnetic field lines. And this is the vectorial equation that I mentioned a while ago. You have the electric field from the anode, which is the substrate holder, to the cathode, which is the target. And so this is electric field. The magnetic field is tangent to this magnetic field line, which is these red dashed lines, okay? And the velocity is perpendicular to these vectors. And since the direction of the magnetic field is changing in the tangent to these red lines, it forces the electron to move spirally along these magnetic field lines, okay? And here you can see the erosion effect on the target. You see that the middle here is more eroded. Here is the sputtering from top down. Sputtering can be done horizontally or vertically, top down, or from the bottom to the top. Here you see another magnet. In some companies, they provide magnetrons, and they tailor the magnets to provide magnetic field lines which are appropriate for the configuration of your system. So it's not, you can just buy a magnetron, expect it to work properly. You really have to look to the dimensions of your system. You have to see if you're using more than one magnetron. If you want to use more than one magnetron, then if you, for example, you want to place one here and you want to place one exactly beside it, then you have to take into account that the polarities have to be switched, because if you have north, south, north, then on another magnet that you place here, the first magnet has to have south, so that you can close the field lines, okay, around the place of the two magnetrons, and you will make a better a dark space here, which is the dark space here, which is the space where we have a higher probability of enhancing the ionization of argon, okay? I think I showed you this maybe in another image, I'm not sure, okay. But anyway, it's in this range that will have higher probability of ionization of the argon, and transform it to argon ions, and can be accelerated to the cathode with disclosure, okay? Here you can see a system which actually incorporates a thermal evaporation system and a magnetron, okay? So you can have a PVD process which has two PVD different processes. It has sputtering, and you also have thermal evaporation source, okay? It's curious. These are some examples of magnetrons, okay? So a magnetron, when you talk about magnetron, it means that you have to have the magnets below the target. Otherwise, if you don't have the magnets, you just call it a source, which has, you can put a target on top. So you put the target here, you have this cup, which you put around, in order to protect the underside of the magnetron, which is copper sheet. It's made of copper. You can have a system with 4 mini magnetrons. Each of them has this kind of shield that you see here, or a shutter, which you can operate it from externally, and you can close or open it. For example, if you're doing multiple sputtering with, for example, if you have 2 magnetron sources, okay, if you want to produce one material, if you want to sputter from this target, you close this one. Then if you want to sputter another material, you close this target and you open that one, okay? So you have, it's important here, you can do 1, 2, 3, 4 different types of materials. For example, if you want to produce those, the CIGS photovoltaic materials that I mentioned in the previous lecture, like the copper, indium gallium selenide, you need to have at least 3 different targets for the copper, indium. And the gallium, gallium has to be a composite, cannot be solid gallium. But for the selenium part, you have to do thermal evaporation. And here, these are targets which are used in the industry. You can see this. This person here is operating a magnetron, which is extremely big. It's very big. Okay, so it's a rectangular rectangular target, which is placed on top of a magnetron. You can see here. Okay. Normally, it's fixed to the bottom part of the magnetron so that the water can flow beneath the target and cool the magnets, okay? Here's the process of co-sputtering. So we're using 2 magnetrons, so we call this co-sputtering, okay? From 2 different materials, we can adjust the angle between the magnetrons and the distance between the magnetrons and your substrate holder. Here's the system with 2 magnetrons. So it's a normal chamber that can be used in the laboratory to produce coatings if you want to study a specific material. So, for example, if you want to do reactive sputtering with oxygen, imagine that you want to do either zinc oxide, for example, either zinc oxide or titanium dioxide. If you want to use, or you can do both. Let's look at this possibility of doing, for example, in some cameras, for photography, you have to have a good lens in order so that the maximum amount of light can enter the lens and go into your CCD if it's a digital camera, or go into the film if it's an analog camera. Okay, and normally on the outer surface of the lens, you have to have a coating, which is a anti-reflecting coating, which means that this anti-reflecting coating enhances the transmission of light through the lens. And for example, like cameras, they have these complex coatings. They can have up to 90 layers of different materials on top of the glass to efficiently enhance the transmission of light through the lens into the sensor, okay, or to the film for analog cameras. That's why they are so expensive, because, and this can be done by sputtering, and you have to, or by thermal evaporation, and you have to do 90 different layers. You know, you stack these layers, and these layers can comprise zinc oxide, can comprise silicon oxide, they comprise titanium dioxide, because you're just playing with the optical properties of these layers, the thickness, and their electric properties and their refractive index properties. Okay, so you can fine tune to enhance this transmission of light, which is really crucial. Okay, for the best cameras for professional photography. So, but let's take the case of titanium dioxide and zinc oxide. So you have to have, if you want to start off with metal targets, you have to place here a zinc target and a titanium target. But since you want to make the oxides, you have to have oxygen as a reactive gas. So you have a bottle of oxygen, you have a mass flow controller with, this is connected to a computer to help you calibrate the amount of gas that you need to put to make titanium dioxide and to make zinc oxide, which can be different. You can use perhaps more oxygen to make titanium dioxide and less oxygen to make zinc oxide, okay? And so the computer has to control the opening of this valve to make the inlet of the appropriate amount of oxygen reactive gas to make any of these 2 materials, okay? Then you have to have the same for the argon, which is the working gas, okay? Here is a top-down approach. So you're sputtering from the top to the bottom, okay? DTS is the distance between the targets and the substrate. Here we have a shutter. For example, if you want to sputter zinc oxide, if zinc is here, you have to open the shutter and close to the other side. Because in this, for example, if your titanium plate is here, then in this process, you're making the position of titanium, which means that you have to rotate your substrate holder and put your substrate directly below the titanium target. To make titanium dioxide, after you put oxygen. Okay. Now, when you sputter from the zinc target, you have to open the shutter, put the shutter on the other part, and place the substrate directly below your zinc target. You introduce the appropriate amount of oxygen and argon, and you do the process again. And both of these targets are connected to a DC power supply, because since zinc and titanium are metals, they are not insulators. You can use a DC power supply. But for example, if you use the silicon target here, then you have to have one DC power supply for the zinc target and radio frequency or alternating current, other type of alternating current power supply for the insulating target. Okay. Now let's, in the industry, you have to save money. And this aspect that I show you, you can see here that this target has already a lot of wear, because on the racetrack of the target, you can see that a lot of material has been removed, because you can see these valleys. Okay, so this is along this road, it's a lot of material which has been removed. And after it reaches the critical depth, you have to replace the whole target. Okay, not the magnetron, but the target, which is screwed to the magnetron. Okay, and to avoid this, in some industries they use a rotating magnetron. It means that your target is a cylinder, okay, and it's rotating, so you have a uniform erosion. You see that there's the thickness of the eroded part is uniform, okay. Contrary-wise, what happens here, where it's mostly located where you have the highest magnetic flux density, okay. And these are some examples of target material suppliers: FHR and GFE in Germany, Jinkoa, Goodfellow in the UK, Kirchhoff in the UK, and in America, which supply target materials. These are some the aspects of some targets. Here, for example, tantalum nitride target, which is important to provide coatings, for example, for dental implants. Because if you make tantalum nitride coatings and they are porous, they can be a base coating for after putting a ceramic material on top of it, for example, hydroxyapatite. Hydroxyapatite is calcium phosphate material, which resembles very closely the structure of bone materials, specifically what we have in your teeth, okay? If you want to produce coatings for wear prevention in cutting tools to the industry, to cut metal sheets, for example, for the automobile industry, these cutting tools are worn very easily. So you have to produce a coating which is very hard and also has lubricating properties. And tungsten carbide is very good to produce these kind of coatings, or titanium carbide also. This is titanium dioxide target, which produces the self-cleaning materials. And you have other kind of examples here. Some process parameters. So like I told you, normally the process is in between 10 to the minus 3 to 10 to the minus 2. In some cases, we can go below 10 to the minus 3, but 10 to the minus 4 will be really very difficult to sustain a plasma. You have to, depends on the working gas that you use. The deposition rate can be between 10 to 100 nanometers per minute, which is 100 more times higher than in diode. So if you use a magnetron, if you place magnets below this, you can increase the deposition rate by a factor of 100, okay? And you also decrease the operating pressure, so you will have less residual gas in the system, so you'll have more, you will have high purity in your films. And normally the deposition temperature is between 60 and 800 degrees. You can, okay, this 60, it's the relative amount, because if you're not using, for example, when I'm making titanium dioxide, if I'm using 500 watts in my cathode, I can easily reach 150 degrees on the samples without any external heating. And this is only due to the transfer of energy from the impinging argon ions to your target material, which will increase substantially the temperature, okay? And you have to take into account. And some advantages again of the magnetron sputtering when comparing to diode. Okay, when you're using a magnetron, so when you're using the magnets, when you place the magnets below the target, you have a higher deposition time. It reduces the electron bombardment on the substrate and allows to extend the application for high vacuum systems with a working lower pressure. And of course, the drawback is the erosion that you produce on the target, which makes an impact on the lifetime of the target. Now we're going to give you some physical theory regarding some physics theory regarding the sputtering process. And we're talking about now the sputter yield. So the sputtering process is characterized by a sputtering yield, which is given by this letter S. So it's a ratio between the ejected atoms or molecules from the target and the incident ions, for example, the incident argon ions, which are incident on your target surface, okay? And this measures the sputtering efficiency. And normally this sputtering yield lies in the range between 0.01 to 4. It really depends on which target material, and it increases with the mass of the metal ions and the energy of the working gas. So higher energies, so higher electric fields, higher potentials from the source, the power supply that we're using will enhance your sputtering yield, okay? So the sputtering yield depends on the energy of the incident ions on the target, the masses of the working gas ions, and of the target atoms, because the masses of the working gas, for example, if you use argon, it has a smaller mass, for example, in comparison to krypton. So krypton can transfer more energy to the target, and in this cascade of collisions can eject more atoms from the target and, towards your samples, okay? So it also depends on the binding energy of the atoms or the molecules on the target material. If in the target these atoms are bonded with very high energy, the bonding energy very high, then it will be very difficult to break this bond, and you have to increase the energy of the impinging argon ions or the other type of ionizing gas which is used for the sputtering, okay? And also depends on the angle of incidence of these guys, of these ions. So for example, here you can see the sputtering yield, the ADS, as a function of the incidence of the working gas ions, okay? So they're not going perpendicularly, but you can see that sometimes for some specific cases, you can have an increase in the sputtering yield for oblique deposition. That's why in some of these examples I showed you, you're seeing oblique deposition and you're not seeing vertical deposition, okay? In this case, it's vertical deposition, but you can, if you place your samples off center, then you will have oblique deposition, okay? And here it's an important graph. Maybe it has a lot of data, I'm sorry for it, but I want to explain you the difference between using different types of working gas. So imagine that you use a nickel target. So imagine that you have a process which is like this, and you use a nickel target, okay? And we're experimenting different working gas. Besides argon, we're introducing other gases. And we want to see which one is more efficient for the process that we want to use, okay? So remember that some gases are more expensive than the others. For example, xenon gas is more expensive than argon, neon is more expensive. Helium gas is also more expensive than argon, and deuterium, which is an isotope of hydrogen, is also very expensive. And here I don't see krypton, but krypton gas is even more expensive. And we want to see, for our process, imagine that if you want to work at around, when you see, so this is 100, 400, at 450 volts. So you want to put power of about, which involves using a potential 400 to 500 volts between your target and your sample holder. So it's this red line that you see here. And here on the vertical scale is the sputtering yield, okay? So you see that for the deuterium, and here you have a log scale. For the deuterium, the sputtering yield is very low at this potential. It's actually higher for helium. And sorry, the deuterium is this curve, and the bottom curve, it's missing here the label, but it's hydrogen. Okay, so hydrogen, deuterium, and helium. Okay, and so you see, if you go from hydrogen to deuterium to helium, the sputtering yield is increasing. Okay, but now if you look at what happens when you use neon, argon, or xenon, if you're working around with a potential of 500 volts, then you can see that the sputtering yield it's almost the same. So here, if you in this zone, you should use the less expensive gas. I'm sorry about the phone. I can avoid it, and I cannot disconnect it. And so you can see that in the range of this voltage, you have almost the same sputtering yield provided by these different gas. So it's better to use the one which is cheaper. Here is an example when you do sputtering on a germanium target, okay? And for germanium, you actually increase the sputtering yield when you produce the sputtering at very oblique angles, okay? So when the angle of incidence is around 80 degrees, you have a very big increase in the sputtering yield. Now, there are some publications which explain you how we can calculate the sputtering yield. And one of the most important papers is given by, by Steinbruckel, a simple formula for low energy sputtering yields. And it was based on the theory that was done by Sigmund in the 60s, okay, from last century. And this paper is from 1995, and the previous paper was from 1969, from Peter Sigmund, okay? And you can calculate this sputtering yield, which here it's given by the S letter, but on this paper it's given by this Y letter, okay? And this sputtering yield, I'm not going very in-depth into this, but you can read the paper if you like, but the sputtering yield is actually proportional to, is dependent, perhaps it's much better to say, on the periodic properties of both the elements of the target and of the gas that's using for sputtering, which is used as a projectile. So Z is the atomic number. ZT is the atomic number of the material of the target, and P is the atomic number of the projectiles. For example, for argon. Okay, and imagine if you're using this is the previous example of the nickel target. So Z is atomic number for nickel, ZT for nickel, and ZP for argon. And the same for the masses of the argon and masses of the elements of the target. Okay, which in this case is nickel. And U is the binding energy of the nickel atoms in the target. Okay, and then you have this alpha function, which is very hard to, it was very difficult to determine at that time. And this is a function. You have this function also here, which is a function of the energy of the ion. So, for example, here, if you use 500 volts, then the energy should be 500 electron volts. So it should be this value of E that you have here. And ETP, this function ETP is given here. It's also a function only of the masses of both the projectiles and which is for example, the argon ions. The mass of the argon and the mass of the target elements, okay? And from this you can calculate, you can predict the sputtering yield of a specific element of the target when you use a specific projectile atom as a working gas. And they made these curves. They made these curves for using different approaches, either from Peter Sigmund and from other scientists that were studying. And so these are results from 3 different groups. And you see that for a ratio between the mass of the target and the mass of the projectile, when it's when one over the other is about 1, there's a good match between the work of all these 3 groups. Okay, but as the mass of the target element is much higher than the mass of the projectiles with argon, xenon, krypton, etc., then they deviate a lot. And so this alpha function, which was drawn from this graph, also gives you a better tendency when it's given by this equation. So you should put this equation here on this part of the alpha function. Okay. But when I was just trying to explain you how you can calculate the sputtering yield. For example, here you can see the prediction of the sputtering yield. But you have to, when it's divided by the experimental sputtering yield. So actually, it's the experimental sputtering yield divided by the theoretical sputtering yield. So the theoretical sputtering yield was calculated by this equation. So this equation is the transformation of this equation that you see here with some corrections using this auto equation, which will give you this equation. And this equation basically has the same parameters, just the atomic numbers of the target and the projectiles, the binding energy of the elements in the target, and the energy of the ions which are impacted on the target. So if you use this equation for the theoretical values, and if you divide it experimentally, it determined sputtering yield by the theoretical one to that equation, you see that the elements that are matched better, the experiment is platinum and ruthenium, and these noble metals like silver and gold have a slight deviation, so the experimental sputtering yield is slightly higher than the predicted one by the theory. But for some elements, like for silicon, tantalum, and titanium, actually the experimental sputtering yield is about half of that of the expected one from the calculated terms. And you know, one thing is also important to see is that the noble metals like silver, gold, platinum, and palladium have a much higher sputtering yield than, for example, titanium and zirconium. So noble metals have a higher deposition rate because they have a higher sputtering yield. Like some elements like silicon, titanium, vanadium, niobium, zirconium have a sputtering yield to 0.5, which can be 5 times less when in comparison with silver and gold, okay? So this comes to what I wanted to say. For example, if you want to make a sputtering from a composite target which has silver, for example, and titanium, and you want to have a coating which in the end has a 50-50% composition, you cannot make the target, for example, using a vacuum melt of these two metals, silver and titanium, to make an alloy. You cannot use 50% of these metals in the target because silver will have a much higher sputtering yield. So you have to put much less amount, 5 times less amount, for example, of silver, okay, then in comparison to titanium, because the sputtering yield of silver at 400 electron volts is about 5 times higher than that of titanium, okay? So as I'm almost at the end, and so as an overview of what I've said so far, you can produce metal films by sputtering, by using metal targets, and you can also produce compound films. You can produce oxides, nitrides, carbides, okay, when using these reactive gases, which are in blue. For oxides, you use oxygen. For nitrates, you can use ammonia or nitrogen. For carbides, you can use methane, acetylene, or other acetone, or you can use other types of compounds or chemical reagents would have this carbon and hydrogen. So in reactive sputtering, you have to be careful because the chemical reaction occurs on the target, which is undesirable. You want the reaction to occur closer to the substrate, not on the target, okay? So you have to avoid the poisoning of the target, okay? This process might poison the targets. For example, you have the surface covered by oxygen, okay? And you have to use the appropriate power supply to produce the coating. Now, the morphology of the coatings, they can vary a lot depending on the pressure that was used for the deposition, and also depends on the ratio of the temperature of the deposition and the melting temperature of the target material. And so I'll be showing you here a graph here. It's from 1977 from Thornton, but this model is still very updated today. And it's where it's used, and you see two horizontal axes. One is the relative temperature. It's the temperature of the deposition divided by the melting temperature of the target material. So it goes from zero to 1. Okay, and on this other horizontal axis, you see here the argon pressure during deposition, here in units of 4. Okay, and if you make a match between the, imagine that if you're using, for example, 4 torr as a pressure of argon, as a working gas, and the relation between you're using low temperature of deposition, so that the ratio between the temperature of deposition and the target melting temperature is 0.2, then you would expect to have your coatings in this transition zone. So what is this transition zone? So in this transition zone, which is labeled by Thornton, you will have a film which has a compact columnar structure with columns separated by just by half a nanometer. Okay, if you increase very much the argon pressure, but using the same ratio of substrate temperature to melting temperature, then you will go into another zone expected for these films. And in this zone 1, you have a columnar structure again, but separated by wide borders and voids. Okay. Now, on the other hand, if you increase the temperature to it's very high temperature, getting closer to the melting temperature, then you'll go through zones 2 and 3, and this is the topography that you will expect from the surface of your films. And zones 2 and 3, the grains will increase in size, and you, instead of columns, you can have very large grains. Okay, and this is an example of sputtering of zinc oxide on the silicon surface. Okay, and this silicon surface is not flat, so it's you see, actually this is what we have. We have a profile of a silicon substrate. Okay, and you have a valley here, and you want to coat zinc oxide on top of it. So here you can see we are viewing this part here. Okay, we're zooming into this side, into the circle, and you can see that the thickness it's not uniform. Here is zinc oxide, and here is the silicon, and you don't have a uniform thick film. Okay, because sputtering sometimes is very complicated for samples which are not flat, which have a three-dimensional facets, and so you will not have very uniform thick coating. Here you can see a zoom of this here of this point here. Okay, and so here you have your target, sorry, your substrate material, which is silicon. You can easily decrease the silicon crystal lattice. And in between the silicon and the growing zinc oxide film, zinc oxide has a hexagonal wurtzite structure. You have this layer here, which is an amorphous layer, and these are the first layers which are being deposited. And since silicon has a diamond structure, which means it's 2 interpenetrating FCC lattice cells, and which is very different in symmetry to that of zinc oxide, which is hexagonal. Okay, and so since the lattice parameters have a big mismatch, the first layers, okay, they do not nucleate very well, and so you need about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 layers in order to start developing this structure with zinc oxide. So, and this is most common, and this happens a lot when you're producing a zinc oxide film. Actually, it's zinc oxide with some amount of aluminum, around 2 or 3%. And this also provides a transparent conductive oxide, which can be used as an electrode. So, as concluding remarks, if you see a comparison between evaporation and sputtering, and we talked about evaporation in the last chapter, so we use low energy atoms, the maximum 1 electron volt. Here we can use high energy atoms, maybe up to 500 electron volts. So it can be 1,000, the energy can be 1,000 times higher than this. It has a high vacuum path, a few collisions, light of sight deposition, and little gas in the film. Because in most cases, you don't use a working gas. You just thermal evaporate from this crucible without using an additional gas, okay? While in sputtering, you have a low vacuum. You have many collisions, you have less line of sight, so it's very difficult to produce uniform thick coatings on complex geometry samples. And you might have some gas in the film because you might incorporate some argon or the projectile gas inside your films. Normally, the crystals are very smaller in sputtering. That's why the films can have more tough if you're working on films for mechanical properties applications. The thermally evaporated films have fewer grain orientation, so they are a bit more textured in terms of crystallinity, while in sputtering you produce polycrystalline films. Okay, better adhesion for sputtering because have higher energy atoms which are producing the film. These are some miniaturized systems for sputtering. For example, for the position of gold on samples previously to going to SEM. When you're using scanning electron microscopy, if your samples are insulating, for example, biological materials or polymers, you really need to coat a very thin layer of gold, about 5-6 nanometers, so that the surface of your sample is conductive and you can see it in the SEM, okay? And normally you just use a very small sputtering chamber. Here is your magnetron, has the magnets, has a very thin gold target, about 0.5 millimeter gold target. They are very expensive. And then you place your samples on the bottom and you sputter down, okay, and you make the gold film. Here's the laboratory equipment, okay. It has, it's very complex, has lots of sensors for measuring the pressure, partial pressures, inlet of gas. Here you can see in the background gas bottles for different gas processes. Then you have the magnetrons, etc. You have to have a very high vacuum. And this is an industrial system, so it's an inline system. For example, for making TFTs for televisions or for computer monitors. So here the glass enters in one side in atmospheric pressure. Then you have a differential pumping system that progressively decreases the pressure from atmosphere down to 1 million times to 10⁻³ millibar. And here's where the magic is done, where the coating is produced. And then the glass is transferred to the outside, okay? And until atmospheric pressure. And this is another example, also for these monitors that you see here. We have the glass, which is going through the process to make the deposition. And here is just, or maybe this graph is not really updated, and it has a log scale. This is the number of publications per year that have been published regarding the sputtering or sputtering techniques or sputtered films. And you see that it increased a lot. And it started in the 40s of last century, and it developed a lot in the last 30, 40 years. And right now it's used in many applications in the industry, in the automobile industry, semiconductor industry, amongst many others, as also for cutting tools applications, like I mentioned. So I finished my talk. Thank you very much for listening to it. If you have any doubts, you can easily contact me by sending me an email. I'll also be available to arrange a Skype meeting or Zoom meeting with you in order to maybe to explain you some of the things that perhaps you didn't understand so well. Thank you very much. Goodbye.